Hi everyone, and welcome to this lesson on Bayes' rule. So Bayes' rule is a pretty useful tool, and you'll want to memorize this one as well. Bayes' rule says that the probability of, if the probability of an event B is positive, then the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So I understand it's a bit of a mouthful just to read, but the important part to notice is that the conditioning switches. So if I want to know the probability of A given B, I can actually write that in a formula in terms of the probability of B given A, which turns out to be really useful because a lot of times we want to know the probability of A given B, but it's a lot easier to find the probability of B given A. The proof of this is just some algebraic manipulation of the definition of conditional probability. Sorry, again, that's probably a mouthful, but let's just walk through it step by step. And the first thing to notice is if the probability of A is 0, this is just kind of trivially true. So if the probability of A is 0 here, then the left-hand side is 0 because conditioning on B makes, it doesn't change anything. The probability is still 0. And also on the other side, the probability of A is 0. So all we're going to get is 0 equals 0, since the right-hand side is 0 times something divided by something, and 0 times stuff divided by stuff is just 0. That's not really the interesting case, but we need to rule out that case. So that's true. Now we want to also consider the case where the probability of A is not equal to 0. And then we're going to use the definition of conditional probability. So the probability of A given B is just the probability of A intersect B divided by the probability of B. If you're not familiar with that, that's just the definition of conditional probability. You can go back and watch the previous lesson, and that's where we covered this definition. Now, since the probability of A isn't 0, we can multiply the right-hand side by the probability of A divided by the probability of A. It's important that the probability of A isn't 0, because we're dividing by the probability of A. So, you never want to divide by 0. And the reason we can multiply the right-hand side by this is that this whole thing is just equal to 1, right? This is just 1. So I'm going to multiply the right-hand side by 1 in a fancy-looking way. And that gives us the probability of A given B is the probability of A intersect B times the probability of A divided by the probability of B times the probability of A. All right, and we could have canceled these two probabilities of A, but instead we're going to use the following. That the probability of A intersect B is equal to the probability of B intersect A. That's because A intersect B and B intersect A are the same set, right? You can commute over the intersection. And the probability of B intersect A divided by the probability of A is the probability of B given A. So what we're going to do is take this set, the probability of A intersect B or B intersect A, however you want to think of it, and this probability of A. So these two. And we can replace that by the probability of B given A. So this equals the probability of B given A, and then there's still a probability of A on top, that's this, and then there's still a probability of B on the bottom, that's this, which gives us Bayes' rule. So the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. It's just essentially using the definition of conditional probability twice. You could also just plug in the definition of conditional probability on both sides and cancel everything. You would eventually get 1 equals 1. So let's look at an example of how we could use this. A survey of your neighbors has revealed that 70% of your neighbors own dogs, 40% of your neighbors own cats, and 50% of the neighbors who own a cat also own a dog. Later, you see a neighbor walking her dog, and you want to know what's the chance that she owns a cat. So to solve this, we're going to start naming some events. And this is a pretty important, technique, and it's useful on the actuarial exam if you're planning to take that. Although it's even useful in a probability course just to solve problems. So we're not given any named events, but we can start naming our own events. So that way we can actually use probability theory to solve the problem. We're going to let D be the name of the event that a neighbor owns a dog. And so by number 1 here, the probability of D is 0.7, since 70% of our neighbors own dogs. And C is the name we'll give to the event that a neighbor owns a cat. So the probability of C equals 0.4, which is number 2. 40% of our neighbors own cats. And last, the information in 3, it's not a new event. So we've already named the event that a neighbor owns a dog or a neighbor owns a cat. And 3 says 50% of our neighbors who own a cat also own a dog. So given that they own a cat, 50%, it's a 50% chance that they own a dog. And therefore, the probability that they have a dog, given that they own a cat, is 0.5. And that is coming from 3. So that's the information we have. P of D given C is 0.5, P of D is 0.7, and P of C is 0.4. Now we want to use that to find the probability that our neighbor owns a cat, given that she owns a dog. That could be written as the probability of C given D. So we're given that she owns a dog. What's the probability she owns a cat? And we can solve this using Bayes' rule. So P of C given D is P of D given C times P of C divided by P of D. And now I have to scroll back up again a little bit, but we just plug in these numbers. So P of D given C, this part here is just 0.5, so we replace that by 0.5. P of C is 0.4, and P of D is 0.7. And we plug those in and we get 0.286, roughly a 29% chance that she also owns a cat. Okay, the next thing we can look at is generalized Bayes' rule. So let's say that A1, A2 to AN is a partition of the sample space omega. Then for any of the events AI, the probability of AI given B is the probability of B given AI divided by the sum over all of the different sets in the partition, j equals 1 to n, of the probability of B given AJ times the probability of AJ. So notice that this is very similar to Bayes' rule itself. And here's Bayes' rule. So I guess we'll hop down to the proof. Bayes' rule would say the probability of AI given B is the probability of B given AI times the probability of AI divided by the probability of B. And what's the difference between the two formulas is only the denominator. So this and this is the only thing that changed. That means the only thing we really need to show here is that those two things are the same. So the probability of B should equal the sum over all of the sets in that partition of the probability of B given AJ times the probability of AJ. And if you remember what a partition is, which will be covered in the lessons on set theory, the union of all these sets equals omega. And in fact, I could just draw a picture here of a partition, because it might be helpful to see in some of this coming up. So if this is omega, a partition means just to chop omega into pieces, essentially. So I just divide the whole set into some pieces. So that could be like A1 and A2 and A3 and A4 and A5, and it doesn't have to be 5. In this proof, we just go to n, so it's just some way to chop up omega into a bunch of pieces. And they're disjoint, right? So there's no overlap between any of these. Each one is its own individual piece. And then if we have a set B, so maybe this here, which I'll color in. In fact, actually, let me use a different color. That might make this more clear. So here's going to be our set B. The some set inside of omega. And if we take B itself, that's equal to B intersect the union of the AJs, because the union of the AJs is the whole space, so nothing interesting is going on there. But we can bring that intersection inside, so it's the union of B intersect each individual set. So here's like B intersect A5 would be this piece of B, and this piece is B intersect A4, and then this is B intersect A2, and this part's B intersect A1. So if I take B and intersect it with each piece of the partition, then union them back up together, I'm going to get all of B. So that's what this line is saying right here. And since these are disjoint and they're equal to b, by the rules of probability, right? Remember the definition says the probability of a disjoint union of sets can be written as the sum. So the probability of b is just equal to the sum from j equals 1 to n of the probability of the b intersect aj's. Then we use the multiplication rule. So the probability of b intersect aj is the probability of b given aj times the probability of aj. And we just substitute that in to each one of these. So the probability of b is equal to the sum from j equals 1 to n of the probability of b given aj times the probability of aj. That's just true for any partition. And that's what we needed to show, because that shows that the two denominators are in fact the same. So back up here we just needed to show this and this were the same. Okay, so once again we've got a fairly complicated looking formula. A lot of times these complicated looking general formulas are easier to use in given examples. So let's actually take an example and see how this general formula is perhaps useful. And right before we do that, let's look at this corollary. So of course A and A complement is a partition of omega. So that's two disjoint sets whose union is everything, since everything's either in A or it isn't. And therefore, the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. So that's just using the generalized formula with the partition A complement. Now let's get to the application. Here we're going to roll one of 3 dice. So we have a 6-sided die, a 10-sided die, and a 20-sided die. We're going to choose a die at random and roll it. So there's a 1/3 chance of getting any one of those 3 dice. And we don't know which one we picked up. So it's like, put on a blindfold, you grab one of these things and roll it, and all you know is that the outcome is a 2. Maybe your friend tells you, a 2 came up. So what's the probability that we chose the 6-sided die? Well, since it was a 2, any one of these 3 die could have been chosen, right? Because there's going to be a 2 on the 10-sided die and a 2 on the 20-sided die, and of course there's a 2 on the 6-sided die. And it seems like it should be more likely that we chose the 6-sided die, because there's a 1 out of 6 chance of getting a 2 on that one, and there's only a 1 out of 10 chance of getting a 2 on the 10-sided die, and an even smaller chance, a 1 out of 20 chance that we would have gotten a 2 if we picked the 20-sided die. So what's the probability that it was on the 6-sided die? Now we can use the generalized Bayes rule to figure this out. And once again, let's use the strategy of naming events. So first of all, we're going to let D6, this one, be the name of the event that we chose the 6-sided die. We'll let D10 be the name of the event that we chose the 10-sided die. And we'll let D20 be the name of the event that we chose the 20-sided die. And finally, we need the name of the event that we rolled a 2, because that's what we were told happened. So let's let A be the name of the event that we roll a 2. Now we're asked to find the probability of D6 given A. So we know we rolled a 2. What's the probability we had chosen the 6-sided die? And the events D6, D10, and D12 form a partition, because we know one of those is going to happen, and there's only a chance, it's only possible that exactly one of those happened. So either we picked the 6-sided die, or the 10-sided die, or the 12-sided die, and for sure one of those things happened. So hopefully in this example, if you're not familiar with partitions, that gives you a sense of what we mean by a partition. It's just a set of events, exactly one of which will occur. So now we use generalized Bayes rule. So the probability of D6 given A is the probability of A given D6 times the probability of D6 divided by the sum over the partition with a similar formula on each one, right? So the probability of A given D6 times the probability of D6 plus the probability of A given D10 times the probability of D10 plus the probability of A given D20 times the probability of D20. Yeah, you usually won't be reading that out loud. Now each one of these has a probability of 1/3, right, of being chosen. So the probability of D6, the probability of D10, and the probability of D20 are all just 1/3. And then if we chose the 6-sided die, there's a 1 out of 6 chance. So we put 1 out of 6 for the probability of getting a 2 if we have the 6-sided die. If we have the 10-sided die, there's a 1 out of 10 chance that it came up with 2. And if we have the 20-sided die, it's a 1 out of 20 chance that it came up with 2. And then a little bit of algebra. So the first thing you can do, if they're all equally likely, you can cancel all the 1/3 on the top and bottom. So that gives us 1/6 over 1/6 plus a 10th plus a 20th. And then getting in common denominators, doing whatever you need to do, you'll find out that the answer is 10 out of 19. So a little greater than a half. So I encourage you to scroll down here and check your understanding. This one is an especially important one for probability in general and for the actuary exam as well. Okay, so I'll see you all in the next lesson.